Okay, so optimization really means finding the maximum or minimum, the biggest or the smallest value. It is the number one application in calculus. In business, we use that all the time in regards to calculus. You want to minimize expenses. You want to maximize profits. And we're even going to see pretty soon that you can deal with dimensions that might relate to having a maximum volume for a certain object and so forth. But let's just jump into this first problem and realize similarities to related rates. It seems like every problem's a word problem with a different setup. It says a farmer has 2,400 feet of fencing, and he or she wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. And what are the dimensions of this field that has the largest area? Let's just say the farmer's saying, you know what? I'm going to put a rectangle together, but I don't want to put just any old rectangle in. I want to put in a rectangle that will have the largest area. So we can draw ourselves a little picture. We can say, well, wow, here's our river. And I hope it's immediately apparent to you that this is a rectangle that's going to use how many sides of fencing? 3, right? I mean, you're not using the side with the river. Now, usually as you go left to right, you talk about a dimension of x. We could do that as well. You're free to use any variable. Vertically, usually we use a y. And in that regard, we're off to a wonderful start. Now, when you're talking about fencing, and you dealt with fencing in the past in geometry, whenever you were finding fencing or the amount of fencing, what in geometry were you finding? A perimeter. And you could say, well, the perimeter of this object would be, this length of x, there are 2 y's, and you'd set this equal to 2,400. Now, immediately what's going to come into many kids' minds is they'll say, well, wait a minute, I thought we were optimizing or maximizing area. And we are. We want to talk about area. And then all of a sudden kids will say, wait a minute, that's peculiar, that's strange. We're talking about perimeter, and yet I'm supposed to optimize area. Well, help me out. If we talked about area just for a moment, what would the area of this rectangle be, even if it only had 3 sides instead of 4? It's still x times y, isn't it? It's still base times height, because area is really counting up the square units. You look at the floor here. We have square tiles all over here. These are 1 square foot units. And even if this wall were to get knocked down behind us, whether it was there or not, we'd still have covering down below, wouldn't we? So that's just getting started. So kids will say, oh, optimizing, maximum, minimums, we're going to take derivatives, right? Which we will. Now, here's the problem, though. You look at a equals x times y, and you think, oh, man, I've got 3 variables. I've got a, area would change depending on x and y. X could be a different length. It could be, bigger or smaller. Y, right here, you could call that the height. That could be different values. Wow, all these things are moving parts, so to speak. They can be different numbers. And to take a derivative now, we'd have to actually go ahead and use the product rule and plow through this. Right now, this is leading really more towards a multivariable problem because you don't have a function with just 1 variable. You think, oh man, if only I could get this area equation down to just 1 other variable. Area on the left, 1 other variable on the right. Well, there is a way. Look at this. There is this obvious, strange, peculiar, wow, we're starting off with the amount of fencing. Couldn't I use that in the problem? And say, now wait a minute, that x is 2,400 minus 2y. And that is what I can substitute in to get a much nicer looking equation. An equation, guys, that right now is only two variables in play. A on the left side, Y on the right. And now, like we've been doing all chapter long, we can determine when A would be the largest, couldn't we? We could find when A is the biggest. Now, rest assured, you can distribute this in, and you could say A is 2,400Y minus 2Y squared. And let's just review a little bit, but also point out that Y can't be as big as we would like. Is it possible to say, oh, this Y dimension, this side of the fence, I'm going to choose it to be 10,000 feet? Could I choose that? No. There are limitations to this problem, just like in the business world. You don't have inexhaustible resources. You just can't say, well, we can use as much money as we want here. Oh, no. No, you're going to have constraints, right? Tell me about maybe some constraints on Y. What do you think about Y? And this is a good thing to review even right now. What's the smallest you could ever have for a side here? Well, it would have to be bigger than what? 0. You can't even equal 0. You won't have a rectangle, will you? You certainly won't have negative values of Y. That wouldn't make any sense whatsoever. That'd be rather silly. And then you'd say, well, wait a minute. What about the largest amount? What do you think we could say Y would have to be less than? Well, 2,400 seems to jump out at you, but Y has to get used twice, doesn't it? So I could even get more picky and say Y actually has to be less than 1,200. You see, Y is going to get doubled up. You might say, oh, Y could be just a little bit smaller than 2,400. No, it couldn't. You have to use 2 lengths of Y in this rectangle. That would say that you've got 4,800 feet of fencing to work with. Why do I bring this up? I do want to point out the obvious. Some of you are going to use calculus in real life later on in real world applications. That gets to be very important. Well, now for maybe the easy part, perhaps. What do? You're going to take your derivative. What is our derivative on the right side? Help me. 2,400 minus 4Y. Well, that's interesting. And then, when you were finding relative maxes, relative mins, and so forth in the past, well, my goodness, what would you always do next? You'd take your derivative and set it equal to 0. Why would you look at that? I'll add a 4Y to both sides. I can divide by 4. And my goodness, would you look at that? Y is equal to 600 feet. Here's the crazy danger that kids can fall into. Please hear this loud and clear. Can I now say, aha, when Y equals 600, we've got our maximum area? No. Just like before, you wouldn't just set your derivative equal to 0 and solve and say, aha, this is where my maximum or minimum would be. You'd have to find out what is what, wouldn't you? What would we always do next? We'd set up a number line. Sometimes kids will say, oh my gosh, Mr. Dabner, do we really have to? Listen, you want to. I'll tell you why. Sometimes you think you're finding a maximum, really you're finding a minimum. Your boss wouldn't be too happy if that happened. Oh, I'll tell you how to maximize our profits. This is what you do. You'd minimize them. You'd be looking for a job, wouldn't you? Right? You got to be real careful. And, and that will come into play in the near future in one of our problems. We're going to see something just like that. We need confirmation. Now all of a sudden these boundaries make more sense. You could say, even if you didn't realize that 1,200 was that upper bound, at the end of the day, you'd say, well, look, we can't go beyond that. You'll get the same answer, even if you didn't put that upper boundary in. But look, we could test something in here. What do you think we'd test with y? Let y equal maybe 100. Maybe over here, test y equals 1,000 maybe. Kids might say, well, gosh, where do I plug it in? Well, into the first derivative. It's the first derivative test. And if you're plugging that in, you plug in 100. Well, 4 times 100 is 400. 2,400 minus 400 is 2,000. That's positive. Oops, I didn't get my pen going here. That's positive. What do you know about your area function? It's going up. Right? Plug in 1,000. Forgot the 0. I said it right. 4 times 1,000 is 4,000. 2,400 minus 4,000, very clearly that's negative. Do we have a minimum or a maximum here? What do you think? Maximum. And that's what we're asked to find, isn't it? You can connect the dots. You can say, hey, look at that. Highest point, top of the mountain as we speak. The endpoints, of course, have to be smaller. I mean, technically, you could even think about what would happen if you plugged in those endpoints. If you plugged in the endpoints, you wouldn't have a rectangle, would you? Plug in y equals 0, plug in y equals 1,200, you wouldn't even have a rectangle to speak of. So, look, here's what we're going to do to just clean this up a little bit. If y is equal to 600, and they're saying, what are the dimensions? You could say, well, look at this picture right here. Y would be 600. What would my x value be? How on earth would I find that? Well, you could say, wait a minute, x was 2,400 minus 2y. If I plug in 600 for my y value, 2 times 600 is 1,200. 2,400 minus 1,200 is 1,200. 1,200. Wow. So I can say for sure that we've got a max here. When y is equal to 600, the first derivative test has shown that to me. What about actually finding that area? The maximum area would be, what do you think? Well, you could multiply the base times the height. 6 times 12 is 72, and you'd need 4 extra zeros, wouldn't you? You'd have that many square feet. Or you could have gone right back up here and said, hey, I could have even plugged in 600 right into that equation and just figured out what my maximum area is. So we've got a lot of information here. What are the dimensions of the field with the largest area? Well, the dimensions would be, what do you think? It's a 600-foot by 1,200-foot rectangle with a maximum area. I know they didn't even ask for this, but you could definitely figure it out. Sometimes they will. Sometimes they're not going to ask for the dimensions. Sometimes instead they're going to say, tell me the maximum area that you can find here. Okay? If you were asked to justify why that's true, you'd have to write a sentence that A prime changes from positive to negative. We doing okay?